Hydroxide is a diatomic anion with chemical formula O-. It consists of an oxygen and hydrogen atom held together by a covalent bond, and carries a negative electric charge. It is an important but usually minor constituent of water. It functions as a base, a ligand, a nucleophile and a catalyst. The hydroxide ion forms salts, some of which dissociate in aqueous solution, liberating solvated hydroxide ions. Sodium hydroxide is a multi-million-ton per annum commodity chemical. A hydroxide attached to a strongly electropositive center may itself ionize, liberating a hydrogen cation, making the parent compound an acid. The corresponding electrically neutral compound HO is the hydroxyl radical. The corresponding covalently bound group O of atoms is the hydroxyl group. Hydroxide ion and hydroxyl group are nucleophiles and can act as a catalyst in organic chemistry. Many inorganic substances which bear the word hydroxide in their names are not ionic compounds of the hydroxide ion, but covalent compounds which contain hydroxyl groups. Hydroxide ion. The hydroxide ion is a natural part of water, because of the self-ionization reaction. H++ O- H2O. The equilibrium constant for this reaction, defined as Kw equals H plus O minus, has a value close to 10⁻14 at 25 degrees Celsius. So the concentration of hydroxide ions in pure water is close to 10⁻7 moles dm-3, in order to satisfy the equal charge constraint. The pH of a solution is equal to the decimal logarithm of the hydrogen cation concentration. The pH of pure water is close to 7 at ambient temperatures. The concentration of hydroxide ions can be expressed in terms of Po, which is close to 14- pH, so Po of pure water is also close to 7. Addition of a base to water will reduce the hydrogen cation concentration and therefore increase the hydroxide ion concentration even if the base does not itself contain hydroxide. For example, ammonia solutions have a pH greater than 7 due to the reaction NH3 plus H plus NH4 plus, which results in a decrease in hydrogen cation concentration and an increase in hydroxide ion concentration. Po can be kept at a nearly constant value with various buffer solutions. In aqueous solution, the hydroxide ion is a base in the Bronsted-Lowry sense, as it can accept a proton from a Bronsted-Lowry acid to form a water molecule. It can also act as a Lewis base by donating a pair of electrons to a Lewis acid. In aqueous solution, both hydrogen and hydroxide ions are strongly solvated, with hydrogen bonds between oxygen and hydrogen atoms. Indeed, the bihydroxide ion H3O2- has been characterized in the solid state. This compound is centrosymmetric and has a very short hydrogen bond that is similar to the length in the bifluoride ion HF2-. In aqueous solution, the hydroxide ion forms strong hydrogen bonds with water molecules. A consequence of this is that concentrated solutions of sodium hydroxide have high viscosity due to the formation of an extended network of hydrogen bonds as in hydrogen fluoride solutions. In solution, exposed to air, the hydroxide ion reacts rapidly with atmospheric carbon dioxide, acting as an acid, to form, initially, the bicarbonate ion, Ol- plus CO2HCO3-. The equilibrium constant for this reaction can be specified either as a reaction with dissolved carbon dioxide or as a reaction with carbon dioxide gas. At neutral or acid pH, the reaction is slow, but is catalyzed by the enzyme carbonic anhydrase, which effectively creates hydroxide ions at the active site. Solutions containing the hydroxide ion attack glass. In this case, the silicates in glass are acting as acids. Basic hydroxides, whether solids or in solution, are stored in airtight plastic containers. The hydroxide ion can function as a typical electron pair donor ligand, forming such complexes as Al4-, It is also often found in mixed ligand complexes of the type MLXYZ+, where L is a ligand. The hydroxide ion often serves as a bridging ligand, donating one pair of electrons to each of the atoms being bridged. As illustrated by Pb2,3+, metal hydroxides are often written in a simplified format. It can even act as a 3-electron pair donor, as in the tetramer PTMe3OH4. When bound to a strongly electron-withdrawing metal center, hydroxide ligands tend to ionize into oxide ligands. For example, the bichromate ion HCrO4- dissociates according to O3CrOH- CrO4 2- H+ with a pKa of about 5.9. Vibrational spectra. The infrared spectra of compounds containing the O functional group have strong absorption bands in the region centered around 3,500 cm-1. The high frequency of molecular vibration is a consequence of the small mass of the hydrogen atom as compared to the mass of the oxygen atom, and this makes detection of hydroxyl groups by infrared spectroscopy relatively easy. A band due to an O group tends to be sharp. However, the bandwidth increases when the O group is involved in hydrogen bonding. A water molecule has an O bending mode at about 1,600 cm-1, so the absence of this band can be used to distinguish an O group from a water molecule. When the O group is bound to a metal ion in a coordination complex, an M-O bending mode can be observed. For example, in SN6 it occurs at 1065 cm-1. The bending mode for a bridging hydroxide tends to be at a lower frequency, as in Cu2Cu2+. M-O stretching vibrations occur below about 600 cm-1. For example, the tetrahedral ion Zinc 2- has bands at 470 cm-1 and 420 cm-1. The same ion has an zinc bending vibration at 300 cm-1. Applications: sodium hydroxide solutions, also known as lye and caustic soda, are used in the manufacture of pulp and paper, textiles, drinking water, soaps and detergents, and as a drain cleaner. Worldwide production in 2004 was approximately 60 million tons. The principal method of manufacture is the chlor-alkali process. Solutions containing the hydroxide ion are generated when a salt of a weak acid is dissolved in water. Sodium carbonate is used as an alkali, for example, by virtue of the hydrolysis reaction CO32- plus H2OH CO3- plus O-. Although the base strength of sodium carbonate solutions is lower than a concentrated sodium hydroxide solution, it has the advantage of being a solid. It is also manufactured on a vast scale by the Solvay process. An example of the use of sodium carbonate as an alkali is when washing soda acts on insoluble esters, such as triglycerides, commonly known as fats, to hydrolyze them and make them soluble. Bauxite, a basic hydroxide of aluminium, is the principal ore from which the metal is manufactured. Similarly, goethite and lepidocrosite, basic hydroxides of iron, are among the principal ores used for the manufacture of metallic iron. Numerous other uses can be found in the articles on individual hydroxides. Inorganic hydroxides. Alkali metals aside from NaOH and Co., which enjoy very large-scale applications, the hydroxides of the other alkali metals also useful. Lithium hydroxide is a strong base, with a pKb of -0.36. Lithium hydroxide is used in breathing gas purification systems for spacecraft, submarines, and rebreathers to remove carbon dioxide from exhaled gas. 2LiOH plus CO2 Li2CO3 plus H2O. The hydroxide of lithium is preferred to that of sodium because of its lower mass. Sodium hydroxide, potassium hydroxide and the hydroxides of the other alkali metals are also strong bases. Alkaline earth metals beryllium hydroxide B2 is amphoteric. The hydroxide itself is insoluble in water, with the solubility products log K *SP of -11.7. Addition of acid gives soluble hydrolysis products, including the trimeric ion B336 3+, which has O groups bridging between pairs of beryllium ions making a 6-membered ring. At very low pH the aqua ion B4 2+ is formed. Addition of hydroxide to B2 gives the soluble tetrahydroxoanion B4 2-. The solubility in water of the other hydroxides in this group increases with increasing atomic number. Magnesium hydroxide Mg2 is a strong base, as are the hydroxides of the heavier alkaline earths, calcium hydroxide, strontium hydroxide and barium hydroxide. A solution, suspension of calcium hydroxide is known as lime water and can be used to test for the weak acid carbon dioxide. The reaction California 2 plus CO2 California 2 plus HCO3 minus plus O minus illustrates the strong basicity of calcium hydroxide. Soda lime, which is a mixture of NaOH and California 2, is used as a CO2 absorbent. Boron group elements. The simplest hydroxide of boron B3, known as boric acid, is an acid. Unlike the hydroxides of the alkali and alkaline earth hydroxides, it does not dissociate in aqueous solution. Instead, it reacts with water molecules acting as a Lewis acid, releasing protons. B3 plus H2O, B4 minus plus H plus. A variety of oxyanions of boron are known, which, in the protonated form, contain hydroxide groups. Aluminium hydroxide Al3 is amphoteric and dissolves in alkaline solution. Al3 plus O minus, Al4 minus in the Bayer process for the production of pure aluminium oxide from bauxite minerals. This equilibrium is manipulated by careful control of temperature and alkali concentration. In the first phase, aluminium dissolves in hot alkaline solution as Al4 minus, but other hydroxides usually present in the mineral, such as iron hydroxides, do not dissolve because they are not amphoteric. After removal of the insolubles, the so-called red mud, pure aluminium hydroxide is made to precipitate by reducing the temperature and adding water to the extract, which by diluting the alkali, lowers the pH of the solution. Basic aluminium hydroxide AlO, which may be present in bauxite, is also amphoteric. In mildly acidic solutions, the hydroxo complexes formed by aluminium are somewhat different from those of boron, reflecting the greater size of Al versus B. The concentration of the species Al 1332 7+ is very dependent on the total aluminium concentration. Various other hydroxo complexes are found in crystalline compounds. Perhaps the most important is the basic hydroxide AlO, a polymeric material known by the names of the mineral forms boehmite or diaspore, depending on crystal structure. Gallium hydroxide, indium hydroxide and thallium hydroxides are also amphoteric. Thallium hydroxide is a strong base. Carbon group elements. Carbon forms no simple hydroxides. The hypothetical compound C4 is unstable in aqueous solution. C4HCO3- plus H3O plus HCO3- plus H plus H2CO3. Carbon dioxide is also known as carbonic anhydride, meaning that it forms by dehydration of carbonic acid H2CO3. Silicic acid is the name given to a variety of compounds with a generic formula SiOX4-2xN. Orthosilicic acid has been identified in very dilute aqueous solution. It is a weak acid with pKa1 equals 9.84, pKa2 equals 13.2 at 25 degrees Celsius. It is usually written as H4CO4, but the formula CO22 is generally accepted. Other silicic acids such as metasilicic acid, disilicic acid, and pyrosilicic acid have been characterized. These acids also have hydroxide groups attached to the silicon. The formulas suggest that these acids are protonated forms of polyoxyanions. Few hydroxo complexes of germanium have been characterized. Tin hydroxide SN2 was prepared in anhydrous media. When tin oxide is treated with alkali, the pyramidal hydroxo complex SN3- is formed. When solutions containing this ion are acidified, the ion SN34 is formed together with some basic hydroxo complexes. The structure of SN34 has a triangle of tin atoms connected by bridging hydroxide groups. Tin hydroxide is unknown but can be regarded as the hypothetical acid from which stanates, with the formula SN62-, are derived by reaction with the basic hydroxide ion. Hydrolysis of Pb2+ in aqueous solution is accompanied by the formation of various hydroxo-containing complexes, some of which are insoluble. The basic hydroxo complex, Pb6O6-4+, is a cluster of 6 lead centers with metal-metal bonds surrounding a central oxide ion. The 6 hydroxide groups lie on the faces of the 2 external Pb4 tetrahedra. In strongly alkaline solutions, soluble plumbate ions are formed, including Pb6(2-). Other main group elements in the higher oxidation states of the elements in groups 5, 6 and 7. There are oxoacids in which the central atom is attached to oxide ions and hydroxide ions. Examples include phosphoric acid H3PO4 and sulfuric acid H2SO4. In these compounds, one or more hydroxide groups can dissociate with the liberation of hydrogen cations, as in a standard Bronsted-Lowry acid. Many oxoacids of sulfur are known, and all feature O groups that can dissociate. Telluric acid is often written with the formula H2TeO4-2H2O, but is better described structurally as Te6. Orthoperiodic acid can lose all its protons, eventually forming the periodate ion IO4-. It can also be protonated in strongly acidic conditions to give the octahedral ion I6+, completing the isoelectronic series E6Z. E equals Sn, Sb, T, I, Z equals -2, -1, 0, +1. Other acids of iodine that contain hydroxide groups are known, in particular in salts such as the mesoperiodate ion that occurs in K4I2O8 8H2O. As is common outside of the alkali metals, hydroxides of the elements in lower oxidation states are complicated. For example, phosphorus acid H3PO3 predominantly has the structure OP2, in equilibrium with a small amount of P3. The oxoacids of chlorine, bromine and iodine have the formula O2A, where N is the oxidation number, +1, +3 or +5, and A equals Cl, Br or I. The only oxoacid of fluorine is F. When these acids are neutralized, the hydrogen atom is removed from the hydroxide group. Transition and post-transition metals. The hydroxides of the transition metals and post-transition metals usually have the metal in the +2 or +3 oxidation state. None are soluble in water, and many are poorly defined. One complicating feature of the hydroxides is their tendency to undergo further condensation to the oxides, a process called olation. Hydroxides of metals in the +1 oxidation state are also poorly defined or unstable. For example, silver hydroxide Ag decomposes spontaneously to the oxide. Copper and gold hydroxides are also unstable, although stable adducts of CuOH and AuOH are known. The polymeric compounds M2 and M3 are in general prepared by increasing the pH of an aqueous solutions of the corresponding metal cations until the hydroxide precipitates out of solution. On the converse, the hydroxides dissolve in acidic solution. Zinc hydroxide Zinc-2 is amphoteric, forming the zinc cation Zinc-42- in strongly alkaline solution. Numerous mixed ligand complexes of these metals with the hydroxide ion exist. In fact, these are in general better defined than the simpler derivatives. Many can be made by deprotonation of the corresponding metal aquo complex. LNM plus B LNM plus BH plus vanadic acid H3VO4 shows similarities with phosphoric acid H3PO4, though it has a much more complex vanadate oxoanion chemistry. Chromic acid H2CrO4 has similarities with sulfuric acid H2SO4. For example, both form acid salts A+, HMO4-. Some metals, e.g., V, Cr, Nb, Ta, Mo, W, tend to exist in high oxidation states. Rather than forming hydroxides in aqueous solution, they convert to oxoclusters by the process of olation, forming polyoxymetallates, basic salts containing hydroxide. In some cases, the products of partial hydrolysis of metal ion, described above, can be found in crystalline compounds. A striking example is found with zirconium. Because of the high oxidation state, salts of Zr4+ are extensively hydrolyzed in water even at low pH. The compound originally formulated as ZrOCl28H2O was found to be the chloride salt of a tetrameric cation, Zr4816, 8+, in which there is a square of Zr4+ ions with two hydroxide groups bridging between Zr atoms on each side of the square and with 4 water molecules attached to each Zr atom. The mineral malachite is a typical example of a basic carbonate. The formula Cu2CO32 shows that it is halfway between copper carbonate and copper hydroxide. Indeed, in the past the formula was written as CuCO3Cu2. The crystal structure is made up of copper, carbonate and hydroxide ions. The mineral atacamite is an example of a basic chloride. It has the formula Cu2Cl3. In this case, the composition is nearer to that of the hydroxide than that of the chloride CuCl2,3Cu2. Copper forms hydroxyphosphate, arsenate, sulfate and nitrate compounds. White lead is a basic lead carbonate, 2Pb2, which has been used as a white pigment because of its opaque quality, though its use is now restricted because it can be a source for lead poisoning. Structural chemistry. The hydroxide ion appears to rotate freely in crystals of the heavier alkali metal hydroxides at higher temperatures so as to present itself as a spherical ion, with an effective ionic radius of about 153 pm. Thus, the high-temperature forms of Co and NaOH have the sodium chloride structure, which gradually freezes in a monocynically distorted sodium chloride structure at temperatures below about 300 degrees Celsius. The O groups still rotate even at room temperature around their symmetry axes and, therefore, cannot be detected by X-ray diffraction. The room temperature form of NaOH has the thallium iodide structure. LiOH, however, has a layered structure, made up of tetrahedral Li4 and Li4 units. This is consistent with the weakly basic character of LiOH in solution, indicating that the Li bond has much covalent character. The hydroxide ion displays cylindrical symmetry in hydroxides of divalent metals California, Cd, Mn, Fe, and Co. For example, magnesium hydroxide Mg2 crystallizes with the cadmium iodide layer structure, with a kind of close packing of magnesium and hydroxide ions. The amphoteric hydroxide Al3 has 4 major crystalline forms: gibbsite, biarite, nordstrandite and doylite. All these polymorphs are built up of double layers of hydroxide ions, the aluminium atoms on 2/3 of the octahedral holes between the two layers, and differ only in the stacking sequence of the layers. The structures are similar to the Bauxite structure. However, whereas the Bauxite structure can be described as a close-packed structure in gibbsite, the O groups on the underside of one layer rest on the groups of the layer below. This arrangement led to the suggestion that there are directional bonds between O groups in adjacent layers. This is an unusual form of hydrogen bonding, since the two hydroxide ion involved would be expected to point away from each other. The hydrogen atoms have been located by neutron diffraction experiments on alpha Alio. The OHO distance is very short. At 265 pm, the hydrogen is not equidistant between the oxygen atoms, and the short O bond makes an angle of 12 degrees with the OO line. A similar type of hydrogen bond has been proposed for other amphoteric hydroxides, including B2. Zinc 2 and Fe3. A number of mixed hydroxides are known with stoichiometry A3MiII6, A2MiV6 and AMV6. As the formula suggests, these substances contain M6 octahedral structural units. Layered double hydroxides may be represented by the formula Mz plus 1 minus Xm3 plus X2, Q plus Q, NyH2O. Most commonly, Z equals 2, and M2 plus equals California 2 plus, Mg2 plus, Mn2 plus, Fe2 plus, Co2 plus, Ni2 plus, Cu2 plus or Zinc2 plus, hence Q equals X.